Hello, my name's Dan Charman and I'm really interested in the causes of climate change on timescales of hundreds of years to several millions of years. We call the last 2 million years the Quaternary period, and it's this period of time that's seen some really big climate changes. I'm here on a hound tour in Dartmoor, and around us what we see today is evidence of cold past climates and also warmer past climates. On the slopes around me we can see tumbled, jagged rocks, and all of these have been caused by much colder climates from about 20,000 years ago during the last ice age. In this video I'll explore with you how climate change is affected by natural factors. Some of these are highly unpredictable and some are very predictable, but these changes together create natural variability in the climate system. Over the last 2.6 million years, the climate has been affected by a range of types of forcing factors. On long time scales of several thousands of years, these are highly predictable because they are driven by the way the Earth moves around the Sun. On shorter time scales of a few hundred years, the causes are much more unpredictable. The main changes over thousands of years are predictable and are caused by variations in the shape of the Earth's orbit and the angle and location of its axis. Milutin Milankovic, a Serbian scientist with wide-ranging expertise and skills, proposed that the changes in the intensity of solar radiation received from the Earth were affected by three fundamental factors. The first of these is called eccentricity, shown here as E, a period of about 100,000 years in which the nearly circular orbit of the Earth changes into a more elliptical orbit. When the orbit is circular, the distribution of energy is equal throughout the year. When it is fully elliptical, the Earth is slightly closer to the Sun sometimes, so it receives more energy at that time of the year. The second factor is called obliquity, shown here as T, a period of about 41,000 years when the Earth's axis tilt varies between 21.5 and 24.5 degrees. This also changes the distribution of solar radiation on the planet. Greater tilt means more insolation at the poles during the summer season, for example. The final factor is called precession, shown here as P, a period of approximately 23,000 years where the Earth's axis wobbles like a spinning top. As it wobbles, the timing of the seasons changes. For example, 11,000 years ago, the northern hemisphere was tilted towards the Sun at the same time as the Earth is at its closest point to the Sun. This meant that there was a greater difference between summer insolation and winter insolation, causing much more seasonal climates. So, if the changes in the Earth's orbit are totally predictable, why can't we predict natural variability precisely? Well, the answer partly lies in the kind of Earth system feedbacks that were discussed in week 1, but it also lies in other short-term influences on climate variability. To understand and assess the impacts of these other influences, we need evidence of past climate change. We do, of course, have access to a wide variety of data to reconstruct climate change over the last few hundred years, instrumental records and information from satellites in more recent years. But to go further back in time, to multiple hundreds of years or thousands of years, we need to use so-called proxy records from places like ice cores and even here in tree rings.
Hi, I'm Ewan Woodley and I'm a climate change specialist here at the University of Exeter. Trees are fantastic archives of past climate. Let's go and find out more. When a tree bursts into leaf in spring, it starts to photosynthesize. Now those sugars that are produced through photosynthesis eventually form wood, and throughout the summer a new layer of wood wraps itself around the tree, and it's this that's called a tree ring. Come autumn, when the day length starts to shorten and the temperature falls, the tree shuts up shop for the winter, ready to burst into action the following spring. So how do we take a sample without chopping down the tree? Well, we use something like this, which is an incremental borer. Essentially, this sharpened piece of metal allows us to remove a core from the tree without harming it too much. Now, the width of these annual tree rings varies year on year, and that's because the rate of photosynthesis depends on what the weather's doing. In a cool or cloudy summer, the trees, much like us, are less than enthusiastic. But when we have a really warm and a really sunny summer, the tree goes mad and its rate of photosynthesis soars, and that's what gives us a really wide ring. On the face of it, brilliant. If we know when we sampled the tree, we can count back the years and see what the weather was doing in each year. But enter two rather large problems. First, how do we actually know that we can trust this tree? For all we know, it might have been attacked by insects, or one of its neighbours might have died and given it the opportunity to steal more nutrients and grow more. And second, this tree isn't actually very old. If we look at the tree rings, we know that weather records go back further than this. So you might ask the question, what's the point? This is where the beauty of tree ring science comes in, and it's called the principle of cross-dating, and it has two massive advantages. Advantage number one, although all of the trees behind us here are growing at different rates, they all show similar patterns in their ring widths. So consult a few neighbours and we might get a better idea of what the climate's doing. Advantage number two, when we've gone back as far as possible with living trees like the ones behind us here, we can actually overlap those patterns of ring widths with their ancestors, wood that's lying on the floors of forests or submerged in lakes or found within peat bogs. Now, this really powerful method has allowed us to reconstruct climate variables such as temperature and precipitation over large parts of the last millennium and even further back in time. Now, whilst it's not without its drawbacks, there's no doubt that tree rings have made a massive contribution to our knowledge and understanding of past climate variability.
Data from sources such as tree rings and ice cores can help us reconstruct how climate has changed in the past. But it can also help us understand the natural yet unpredictable forcing factors that lie behind that climate change. First, there are variations in the amount of energy that the sun puts out, so-called solar variability. We know, for example, that during the medieval period, the sun was more active than it was during the subsequent few hundred years known as the Little Ice Age. And that partly explains why Houndtor was a much better place to farm in the medieval than it was during the subsequent centuries. But it wasn't just the sun that changed from medieval to Little Ice Age and caused that dramatic climate change. Volcanoes also played a role and are a main cause of short-term, highly unpredictable changes in weather and climate. Throughout Earth's history, volcanic eruptions have had a significant impact on global temperatures, and there is evidence that greater global volcanic activity also helped push places like Houndtor from medieval warmth to Little Ice Age cold. Volcanoes generally cause cooling of climate, at least on short timescales. In 1991, Mount Pinatubo in the Philippines erupted. Ash clouds from major eruptions block out solar radiation by launching aerosols high into the stratosphere. The ash cloud spread aerosols all around the globe. These reflect solar radiation back into space, cooling the planet. In the years following Mount Pinatubo, global temperatures dropped by 0.5 degrees Celsius. Volcanism and solar activity, key natural factors that affect our changing climate. We can match climate data from ice cores and tree rings to events and cycles related to these natural forcing factors. However, when we look at our climate record in the last 100 to 150 years, these natural forcing factors fail to explain what's happening to global temperatures. Let's look at one of the most famous or infamous plots of climate change, the so-called hockey stick curve. What this shows us is that temperatures have increased dramatically over the last 100 or 150 years in a way that can't be explained by solar variations and volcanic activity. If we overlay on that plot atmospheric carbon dioxide concentrations, we can infer that perhaps CO2 is the big new player in this story. And graphic illustrations of the influence of climate on past populations should give us some pause for thought about how we are now affecting climate in the future and how that future climate might come back and affect us.